Hello 9th class students. The next chapter which I am going to start for you is atoms and molecules. See, when it comes to SSC examination, this chapter is very important, because in the next year you have a chapter by name structure of an atom, which is again a high weightage chapter, and when it comes to intermediate, again this chapter repeats. Okay, so the foundation which you will be receiving in the 9th class is going to help you understand the chapters in the later stages or the advancement of the topics in atoms and molecules. Okay, so I'm going to start atoms and molecules. It's a bit lengthy chapter and I'll be going in very detail for this one, so watch the videos which I'm giving you now.
Hello friends, this video on atoms part 1 is brought to you by examfear.com. No more fear from exam. Topics to be covered in this lesson are discovery of electron, proton and neutron and their characteristics, Thomson's model of atom, Rutherford's model of atom, atomic spectra, spectral lines, Bohr's theory of atom, Bohr's model of hydrogen atom, and de Broglie's explanation of Bohr's postulate of quantization. So as the name suggests, we are going to talk about atoms. The name is very much familiar with all of you, right? Every time we talk of anything, we talk of matter, we talk of molecules, and therefore we talk of atoms. So now in this lesson, we will exhaustively talk only about atoms. What is an atom? How was an atom discovered? And several other things related to the structure of an atom. How does an atom look like? What does an atom consist of? So this is all which we will talk about in this lesson. Now, if you look at what have we been studying in physics, you would see that we started with, in your very earlier lessons, we talked about electrostatics, electricity, then we came to magnetism, then we tried to relate electricity and magnetism, how both of them are related. Then we gradually proceeded and we spoke about electromagnetic waves. Thereafter, we talked about waves as such. Then we proceeded again and we talked about optics. Thereafter, we talked about the dual nature of matter and radiation. That is, every object which we see in this world can behave as a particle as well as it can behave as a wave. So that is all that we have been progressing so far. So now here in this lesson, we will talk about atoms, because it is very much necessary that you should know about atomic structure. What is the structure of an atom, so that it will help you to go further. As I told you that presently what is true is nothing but your quantum physics. The physics which tells that everything which we see around us has dual nature. That is, it has particle nature as well as wave nature. Okay, so let us forget all that and let us start and see what is an atom. So let's start with the very basic definition of an atom. Atom is the basic unit of matter that consists of a dense central nucleus surrounded by a cloud of negatively charged particles. So that is how we have been defining atoms since ages, right? That is how all of us know atom as. What is atom? It is nothing but the basic unit of matter. Whenever we look at any object, it is nothing but matter, right? Matter is made up of molecules, and molecules in turn is made up of atoms. So atom is a basic unit of matter. It consists of a nucleus, right? You have, this is the picture of an atom which we have in our mind. This is the nucleus, and then you have the electrons which revolve around the nucleus, right? And the nucleus is dense, it is massive, it has good amount of mass, and the nucleus again consists of the neutron and the proton, right? So that we all know these basic things about atom. Okay, so when we talk about an atom, you can imagine how small an atom would be, because whenever we talk about atom, we talk in terms of units like angstrom or Fermi, which I have mentioned here. And what is 1 angstrom? You all know that 1 angstrom is 10 to the power minus 10 meters. So you can imagine how small it is. It is 10 to the power minus 10 meters. right? Normally when we talk about lengths, which are like visible to us, we talk about meters, we talk in terms of meters, centimeters, millimeters. Till then it is fine. But when we talk about the size of atom, we talk in terms of Fermi, which is again, how is Fermi related to angstrom? 1 angstrom is again 10 to the power 5 Fermi, right? So atom is that small. So if you take this as an example, like let us suppose if we assume that a cricket ball represents a nucleus. If the cricket ball is a nucleus, then the radius of the atom would be about 5 kilometers. So you know how much is 5 kilometers? Right? It is quite a long distance. So you can imagine this, why this statement has been quoted here, just to ensure or just to show you that how small the nucleus is when compared to the size of the atom. That means if this ball is your nucleus, then your atom is, the radius of the atom is 5 kilometers. That means from here some 5 kilometers, I mean that is beyond the scope of the screen. 5 kilometers is a long distance, right? So that big would be your atom. And when we talk about atom, we anyways know that atom itself is very small. So you can just imagine, or you can just compare the size of the nucleus to that of the atom. So let us now see, why are we studying atom? What is the necessity to study atom? Well, I mean, it is needless to say that everything that we see around us, starting from anything, is nothing but made up of atom, right? Also, when you study atoms, it helps you to understand the various kinds of chemical reactions which take place. I mean, this is the part which will be better taken care of in your chemistry lessons, because there you would have seen, I mean, in your chemistry lessons you would have seen that if you know the atomic structure, if you know the electronic configuration of each element, it helps you to understand the chemical reaction. It is you who is able to say that what will happen if sodium reacts with chlorine, what will happen if hydrogen reacts with oxygen, right? So that means if you are aware of the atomic structure, because only when you understand the atomic structure, only then you can understand how the electrons are distributed in an atom, right? So if you understand that electronic distribution, then you know the electronic configuration of each element. And once you are aware of the electronic configuration, you can understand the various chemical reactions which take place, because everything that happens around us is nothing but different kind of reactions taking place. The tablets which you take, or the medicines, capsules or tablets, whatever you take when you fall ill, what are they? They are also formed by mixing different kinds of substances, right? They all have different composition. So studying atom is a very basic thing. If you know the atomic structure, learning on that, top-ups on that will help you to understand many more things which happens in our day-to-day life. So starting from any small object which you see around yourselves, whether being it an eatable or a ball or a car or whatever, everything is made up of atom. So studying atom is necessary, right? So without wasting any further time, let us quickly look at the history of atom. We will not spend much time on this slide. We will just see how atom was discovered. Long back, somewhere around 500 BC, there was a Greek philosopher, a Greek as well as Indian philosopher named Democritus, who coined the term atom. He named it atom. What is atom? What is the meaning of this term atom? It means indivisible or uncuttable, something which cannot be further divided into smaller parts. However, during that time it was considered that atom is indivisible. You cannot further break it down into smaller components. However, later it was found that an atom is also further divisible. That is, atom also was further consisting of electron, proton and neutron. In fact, even after a couple of years, it was found that even those electron, proton and neutron were also further divisible into smaller particles. So, however, during that time, somewhere around 500 BC, it was assumed that it was known to people that atom is uncuttable. So that is why Democritus named it as atom. In 1805, John Dalton proposed the atomic theory. He proposed a theory where he told that every object is made up of atoms and atoms are indivisible. So whatever John Dalton spoke was on same lines as that of Democritus. Again, after a few years came up Faraday with the cathode ray tube experiment somewhere around 1850s. So what was this cathode ray tube experiment? Again, an evacuated chamber was taken. I mean, I have discussed this experiments and all in our previous lesson, that is dual nature, right, where I told you that if he took an evacuated tube and he saw that there was a cathode and there was an anode, and he saw that some rays were coming up from the cathode, because of which he was able to see some glow. So from these cathode ray tube experiment only, later electron was discovered. We have discussed all these things in our previous lesson, so I don't want to waste time again discussing the same things. So again, after a couple of years, as I mentioned, J.J. Thomson discovered electron and he concluded that they were a component of every atom. So J.J. Thomson was the one who told that atom was not indivisible. Atom can be further divided, and he was the one who discovered electron with the help of the cathode ray experiment. With that idea in mind, he was able to discover electron, and he also told that electron was a component of atom. So Thomson proposed his own atomic model, because in his atomic model, atom was no more uncuttable. Atom was now consisting of electrons. Thereafter, somewhere around 1909, another scientist named Rutherford came up with a gold foil experiment. So he proposed a completely new atomic model. So J.J. Thomson was the one to propose an atomic model. After that, Rutherford came up with this experiment, which was very successful, and this Rutherford's model of atom is what is very similar to what we know atom today as. Because earlier, whatever the concepts, earlier, long back, people thought atom is indivisible. So that time they thought that that is correct. But with passage of time, with more and more efforts put in by different scientists, it was found that no, atom was divisible. Similarly, Thomson gave one atomic model which was considered true at that time. But later, when Rutherford performed his gold foil experiment, he found that a new atomic model which laid the basic of the real structure of atom. So Rutherford's atomic model was a very important concept. Thereafter, in 1912, came up Bohr, who proposed a new model of atom. So, though offering a satisfactory model for explaining the spectra of the hydrogen atom, it could not explain the spectra of multi-electron atoms. I'm sure right now you're not understanding any of these, that what is spectra, what is multi-electron atoms. So, in Bohr atom, an electron is considered as a charged particle. Okay. So in first atomic model was given by Thomson. Then Rutherford did one experiment and he told that Thomson's model was not correct. So he gave a new model of atom. However, Rutherford's model of atom was also not completely satisfactory. It could explain many things, but there were many things which it could not explain. So thereafter came up Bohr's model, which could explain the limitations of Rutherford's model. So Bohr's model in that way was better than Rutherford's model. However, Bohr's model also had certain limitations, and those limitations were covered up by the modern or the quantum mechanical model of atom, right? So this is how the atomic structure was discovered. So if you see, it started somewhere around 500 BC when atom was discovered, and then gradually it extended till 1900s. So it took so many years to actually understand that what is the structure of an atom. So even after this, somewhere around 1924, de Broglie hypothesis talked about the dual nature of electron, right? We have spoken about de Broglie's hypothesis in our previous lesson. Yet after this, somewhere around 1926, Schrödinger proposed an equation called Schrödinger equation to describe the electron distribution in space and the allowed energy levels in atoms. So as I told, Bohr's atomic model was quite successful. However, it had certain limitations. So those limitations were covered only by quantum mechanics. What is quantum mechanics? The branch which deals with dual nature of objects. It talks about it says that every object which we see can behave as a particle, it can also behave as a wave, depending upon the circumstance under which we are observing that particle, right? So Schrödinger was an eminent scientist in the era of quantum mechanics. So Schrödinger gave an equation which described the electron distribution in an atom. Right? When I talk about atomic structure, what do I want to know in the structure of an atom? We want to know how the electrons are distributed around the atom. I mean, inside the atom we have a central nucleus and we have electrons revolving around the nucleus. But we want to know how those electrons are distributed around the nucleus. That is the most important question, right? So Schrödinger gave one equation which is popularly known as the Schrödinger equation, which tells us how the electrons are distributed in space and what are the allowed energy levels. So we will talk about energy levels, we will talk about electron distribution as we go ahead. Again, in 1927, Heisenberg proposed the Heisenberg uncertainty principle. So if you see this de Broglie, Schrödinger and Heisenberg, they were all talking about dual nature, right? So they all have entered the quantum era. So in reality, what we see, I mean, we don't see actually, but in reality, the atomic structure is nothing but what was proposed by this quantum mechanical model. So this is how you can see that how much time it takes to know what actually the structure of an atom is, right? So again, around 1932, there was another scientist called Chadwick who discovered neutron. So see, something very surprising that for so many years, there were so many studies and investigations going on atoms, but neutron, which was again another component of atom, was discovered after such a long time. Neutron was discovered very recently, somewhere in 1932. So that means neutron was discovered almost around the time when everybody knew that when quantum mechanics had already come into picture. So neutron was discovered after quite a long time. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again. Hello friends, this video on atoms part 2 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched part 1 before going ahead with part 2. So this was all about the history of atom. So now let us quickly look at the important theories which came up and which gave their opinion on the atomic structure. So the first one was Dalton's atomic theory. So let us quickly look at the Dalton's atomic theory. Dalton said that matter consists of indivisible atoms. That means according to Dalton, we cannot further divide atoms, which was however proved incorrect in later times. The theory said that all the atoms of a given element have identical properties, including identical mass. Atoms of different elements have different mass. Compounds are formed when atoms of different elements combine in a fixed ratio. You would have studied about compounds, elements, mixtures, all these things you would have studied in your chemistry, right? So Dalton basically gave the definition, or he defined the atomic theory more inclined to chemistry, right? Because he talked about atomic number, mass number, formation of compounds. So he talked about all those aspects of atom. So he said that if for one element, all its atoms will have the same mass. Similarly, for a different element, all its atoms will have a different mass, right? Now, when do we have compounds? When atoms of different elements combine in a fixed ratio. He also told that chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. So that means when one substance reacts with another substance, what happens? He told that atoms get reorganized, reorientation of atoms take place, and there is no creation or destruction involved. So the success of Dalton's atomic theory lied on these points. It was successfully able to explain the law of conservation of mass, because he told that all the atoms of an identical element will have the same mass. Law of constant composition, as he mentioned that when atoms of different elements will combine in a fixed ratio, only then compounds are formed. Law of multiple proportion. So these were some of the laws which were very truly or very correctly satisfied by Dalton's atomic theory, and that is why Dalton's atomic theory became a success at that time. However, there were several limitations which were involved with the Dalton's atomic theory. It failed to explain the results of many experiments. For example, what happens when glass is rubbed with silk or fur? Electricity is generated, right? We spoke about it when we were studying about electrostatics. When you rub a glass with silk, what will happen? Electricity gets generated. So people questioned Dalton that you say that whenever two substances react, whenever any reaction takes place, it is because of the reorganization of atoms. So in this case, how is electricity generated? Because you say that no atoms are created, no atoms are destroyed. It is only the reorganization of atoms. So Dalton was unable to explain the formation or generation of electricity in these cases, right? But experimentally, they did happen, right? When you place a comb near small bits of paper, the papers get attracted towards the comb. Similarly, when you rub a balloon on a piece of cloth, and then when you try to bring it towards the wall, it sticks to the wall. So all these things where there was some generation of something was involved, Dalton was not able to explain it with his atomic theory. So this was the reason of failure of Dalton's atomic theory, because these experiments were something which everybody was actually observing in nature. It was actually happening, right? That means there has to be reason behind it, but Dalton's atomic theory could not explain that reason. And this became the reason of failure of Dalton's atomic theory. It failed to explain subatomic particles that were discovered in the 20th century. So Dalton's atomic theory told that atom was the smallest particle. There cannot be anything inside atom. But later, in the 20th century, it was found that atom was further divided into electron, proton and neutron. So this theory could not explain those subatomic particles. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again. Hello friends, this video on Atoms Part 3 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched Part 1 and Part 2 before going ahead with Part 3. So thereafter came up some other atomic models. As I mentioned in the first slide, that after Dalton's atomic theory came up another atomic theories. The first one being the Thomson model of atom. It came somewhere around 1897. Thereafter came the Rutherford's nuclear model of atom around 1909, which was again followed by Bohr's model of atom in 1912. And this was followed by the quantum model of atom. So these are the 4 atomic models which we will discuss in this lesson. So quantum model of atom is the one which is presently accepted and is considered to be the real model, right? So let us first look at the Thomson model of atom. What did this model say? This model stated that an atom possesses a spherical shape in which the positive charge is uniformly distributed. So according to Thomson's model, inside the atom is spherical in shape, and inside the sphere we have positive charge distributed uniformly everywhere. So the positive charge is present everywhere inside the atom. And what about the negative charge? That is the electrons. The electrons are embedded into it so as to give the most stable electrostatic configuration. That means, as such, if you look at this figure, it will be clear to you. That means this pink colored sphere has positive charge distributed all over it. I mean, the entire sphere is a dense positive charge sphere, and the electrons are embedded somewhere. And the electrons are embedded in such a way that it gives it a stable arrangement. So this was Thomson's model. So this model was often called as plum pudding model, or raisin pudding model, or watermelon model. It was known as watermelon model because it resembled watermelon. I mean, if you think of it, if you look at the watermelon, how does it look like? It has the small seeds embedded here and there, right? So similarly, electrons were embedded here and there inside the atom. So that is why it got these kind of names like plum pudding, raisin pudding, because inside the pudding, that pudding is nothing but the uniform distribution of positive charge, and inside that pudding you have plum here and there. Similarly, you have raisins here and there. So that is why this Thomson's model of atom was known by all these alternative names. This model could successfully explain the overall neutrality of the atom, but was not consistent with the results of later experiments. That means why this model was successfully accepted by people, because it could explain that even though atom consists of positive charge as well as negative charge, but still overall the atom is neutral. So it could explain that, but it could not explain some of the results which were discovered later, because this model just spoke about how the positive charge and negative charge is distributed inside the atom. But later, when proton, neutron, everything were discovered separately, then there were certain results which could not be explained by this model of atom. So even Thomson's model of the atom could not be a big hit. Well, make a note of this point that neutron and protons were not discovered at this time when Thomson had proposed this model. So right now people were just talking about the model of the atom, and since electron was discovered, so people were talking about electrons. So people were considering that since electrons are negatively charged particle, there has to be some positively charged particle. So they never named it as proton or neutron or something, because they were not discovered by that time. So here people were only talking about positive charge, atom and electron, right? Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again. Hello friends, this video on atoms part 4 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 3 before going ahead with part 4. So after the failure of the Thomson's model, after a couple of years came up Rutherford's model of atom, and Rutherford's model of atom became a big hit because it was able to explain many properties. I mean, it was able to successfully explain and incorporate many things, because of which it was very easily accepted by people, right? So now, before we talk about the Rutherford's model, I will quickly introduce you to few new terminologies, that is alpha particles, beta particles, gamma rays and X-rays. Why am I introducing these? Because in the experiment which Rutherford had performed, we make use of these particles. So therefore I am giving you just a touch of what are these particles before we start with the Rutherford's model. However, we will discuss in detail about these particles in our next lesson, that is the lesson on nuclei. So here I will just give you the basic definitions of these. Now it happened in 1895 when a scientist named Roentgen showed that when electrons strike a dense metal in the cathode ray tubes, it produces rays which can cause fluorescence in the fluorescent materials placed outside the cathode ray tubes. Since he did not know the nature of this radiation, he named them as X-rays. So this is how X-rays were discovered. It is little similar to the cathode ray tube experiment, right? The same kind of apparatus, and he found that when electrons strike the dense metal, some radiations were produced. Now he did not know much about the nature of the radiation, so he named them as X-rays. So even today we call them as X-rays, right? So he found that these were not deflected by electric and magnetic fields and have a very high penetrating power through matter. And this property of X-rays, that it has got very high penetrating power, makes it very much useful in medical applications, right? You would have seen that if somebody gets a bone fractured or something like that, the doctor asks you to get an X-ray done of that body part. So what happens in an X-ray? When you do an X-ray, those radiations basically have very high penetrating power, so they can penetrate very easily inside your body, and that is how you get a scan of the internal structure of your body part, right? So X-rays have got excellent penetrating power, and they are not deflected by electric and magnetic fields, right? They stay neutral when placed in electric field or magnetic field. Now, there are certain elements which emit radiation on their own, and this phenomenon is known as radioactivity, and such elements are called radioactive elements. Mostly these elements lie they generally have very high atomic numbers in your periodic table. So it is a property which is characteristic to those elements. It doesn't happen with all elements, right? So there are some elements they are capable of emitting radiation even if you don't do anything to them. They are just left on their own and they will emit radiation. So this phenomenon is called radioactivity, and such elements are called radioactive elements. We will talk about radioactivity in detail in our next lesson. Now, these radioactive elements generate three kinds of particles, or you can say three kinds of radiations: alpha particles, beta particles, and gamma rays. So these are the three kinds of emissions that take place during radioactivity. So what are alpha particles? Alpha particles are positively charged helium nucleus. So what is your helium nucleus? With atomic number 2 and mass number 4. So alpha particles are positively charged helium nuclei. What are beta particles? They are negatively charged particles similar to electrons, right? And what are gamma rays? Gamma rays are high energy radiations like X-rays. They are neutral in nature and do not consist of particles. So that is why gamma is known as gamma rays and not as gamma particles, because they do not consist of particles. They are like radiations similar to X-rays, and they are also neutral in nature. So we will, no need to worry much about what are they and from where do these alpha particles come and all those things, because we will discuss them in detail in the next lesson. So for now, you should only know that what is alpha particle, what is beta particle, what is gamma rays, because when we discuss Rutherford's experiment, we will talk about alpha particles. Now, as regards to penetrating power, alpha particles are the least, followed by beta rays and gamma rays. So that means out of alpha, beta and gamma, gamma rays are the ones which has the highest penetrating power, right? So this was a small introduction to alpha and beta particles and gamma and X-rays. So let us now talk about Rutherford's experiment. Now, after the failure of Thomson's atomic model, Rutherford started studying the structure of atom. So he performed an experiment, and this experiment laid the milestone in determining the structure of atom. So what did he do in this experiment? He bombarded very thin gold foil with alpha particles. So this is why I introduced alpha particles, that at least now you know that, okay, what are alpha particles? You can at least visualize them as positively charged helium nucleus, right? So he took some alpha particles and allowed the alpha particles to strike a very thin gold foil. So gold foil is nothing but it is a metal foil, right? How he made this arrangement, if you look at this figure, you can understand that this is your gold foil, and this is a source from where your alpha particles are coming and striking this gold foil. Now, stream of high energy alpha particles from radioactive source, because you need a radioactive source. I mentioned you in the previous slide, right, that what are alpha particles? Alpha particles are emitted by certain elements which have this property of radioactivity. That is, those elements have the property that they emit radiation when they are left on their own. So we take a radioactive source, and then high energy alpha particles are made to strike on the thin foil of gold metal. The thin gold foil has a circular fluorescent zinc sulfide screen around it. If you look here, this is the zinc sulfide screen. It acts as the detector. It will detect the alpha particles which are reaching the screen. So whenever alpha particles struck the screen, a tiny flash of light was produced at that point. That's because this is why a fluorescent screen is used, because so that whenever the alpha particles strike on that screen, a fluorescence is observed. So by looking at that flash of light, we can detect that, okay, this alpha particle had struck at this point. Similarly, that alpha particle struck at that point. So we can understand that where exactly the alpha particles are actually striking, right? So this was the arrangement which was used by Rutherford in his famous experiment. Now, what was the result? What was observed in Rutherford's experiment? So basically, what was Rutherford's aim? His aim was to study the distribution of the number of scattered particles as a function of the angle of scattering. So what are the scattered particles in this case? If you look at the arrangement, you would see that these particles, this collimated beam which you see here, it is nothing but the beam of alpha particle. Now each of these alpha particles were getting scattered in different directions. Now this angle by which each alpha particle was getting scattered is known as the angle of scattering. So Rutherford wanted to study the distribution of these alpha particles as a function of the angle of scattering. That means, let us suppose the angle of scattering, for an angle of scattering of 30 degrees. He wanted to see how many alpha particles scattered by 30 degrees. Again, he wanted to know how many alpha particles scattered by 50 degrees, how many alpha particles scattered by 70 degrees, right? So he wanted to see, and how was he able to know that? Because whenever an alpha particle reached this detector, there was a flash. So let us suppose there was one flash, again another flash, again another flash. That means there were like total 3 flash. That means there were 3 alpha particles which reached these point. That means there are 3 alpha particles which were scattered by this angle of scattering, right? You're getting my point? So this is how this experiment helped Rutherford to actually study that how many number of alpha particles which got scattered as a function of the angle of scattering. Now, using the data which he experimentally collected, he found that if he plotted a graph taking number of scattered particles on the y-axis and scattering angle along the x-axis, he found a graph of this sort. That means, as the angle of scattering increased, the number of alpha particles decreased. That means there were very few alpha particles which were scattered by a greater angle, right? So when will be the scattering angle large? Scattering angle large. Scattering angle large means, what does it mean? Let us suppose if this is my alpha particle, this is my alpha particle, right? This alpha particle approaches this object. Now, if this alpha particle gets scattered by a very large angle, that means this alpha particle is highly repelled by this object, because if the alpha particle would have been attracted by the object, it would have not scattered, it would have got attracted towards the object and gone like this. Now, if an alpha particle is getting scattered by a very large angle, that means that alpha particle is experiencing a strong repulsive force. So that means for large theta, so somewhere around this portion, when theta is large, that means the alpha particle experiences a repulsive force. So what does this graph tells us? This means repulsive force is more. Now from this graph we see that for large theta, the number of alpha particles is very small. That means this implies that very less number of alpha particles are repelled, right? Because there are very less number of alpha particles which are scattered by large theta. Now since there are very less number, therefore there are very less number of alpha particles which are repelled, right? So what does this mean? This means that the dense part inside the atom is very small. That means the atom is not dense everywhere, as was told by Thomson. What did Thomson tell? Thomson's model told that the entire atom consists of positive charge uniformly distributed everywhere, right? So that means according to Thomson, the atom as a whole was dense. But from Rutherford's experiment, it was seen that since very less number of alpha particles are getting repelled, that means the dense part inside the atom is located or is localized into a small region, and this dense part was nothing but the nucleus, because the alpha particles are positively charged. So alpha particles are getting repelled by a positive charge, can get repelled by a positive charge. So that means this dense part was positively charged and this dense part was known as nucleus. So from this it was discovered that nucleus is only a small portion of the entire atom. So that is how I compared the size of nucleus with the atom in the first screen, right? That where I told that if a cricket ball is your nucleus, then the radius of the atom is somewhere around 5 kilometers. Right? So from this you can see that there were so many alpha particles which were striking the target, but only very few of them got repelled. That means there is only a very small positively charged dense part inside the atom which is known as nucleus. So this nucleus is the only portion which is repelling the incoming alpha particles. Right? So therefore it was concluded that most of the mass of the atom is concentrated at the nucleus, right? So what is the remaining portion of the atom? The remaining portion is empty, and the remaining portion consists of the electrons which are orbiting around the nucleus. So now the question is, how are the electrons arranged, or how is the electron distributed in an atom? So from this part you understood that how Rutherford concluded that nucleus consists of most of the mass of the atom is at the nucleus, and also he concluded that nucleus is only a small portion of the atom. The rest of the atom is empty. The rest of the atom is not dense. It consists of electrons moving around the nucleus. Right? Okay. So from Rutherford's experiment and his observations, what did he conclude? So one point I discussed in the previous slide, right? That since it was found that very few alpha particles got repelled, so it was concluded that that means the positive charge inside the atom is localized in a very small region, and that is why it repelled a very few alpha particles. So what was this force of repulsion between alpha particle and the nucleus? The force of repulsion between the alpha particle and the nucleus was given by the Coulomb's force, that is 1 by 4 pi epsilon naught into charge on alpha particle, that is 2e, because it is helium nucleus. Helium nucleus has 2 electrons. Therefore, the charge on the alpha particles will be 2 into charge of an electron into the charge of the nucleus. So, how many electrons are there in the nucleus? Number of electrons in a nucleus is nothing but the atomic number, that is represented by Z. So, this would be the charge on the nucleus divided by r square, where r is the distance between the alpha particle and the nucleus. So the magnitude and direction of this force of repulsion between the alpha particle and the nucleus changes as the alpha particles comes nearer to the nucleus, right? Okay, so now what did Rutherford finally concluded? So final conclusion given by Rutherford was that since most of the alpha particles passed through the foil undeflected, as I mentioned, only few alpha particles got deflected. Rest of them, they moved through the foil undeflected. So what did this tell? From this he concluded that most of the space in an atom is empty. Right? That is why it did not get deflected, because there was no obstruction inside the atom. So that means most of the space in the atom is empty. His next observation was that a few positively charged alpha particles were deflected. So this we discussed in the previous slide. So for this he concluded that positive charge is concentrated in a very small volume inside the atom that repelled and deflected the positively charged alpha particle, right? And this small positive charge, which was concentrated in a very small volume inside the atom, constituted the nucleus, right? Okay. What else? Calculations by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The best example, the comparison of the cricket ball, right? The radius of the atom is about 10 to the power minus 10 meters, whereas that of the nucleus is 10 to the power minus 15 meters. So if you see, there's a difference of 10 to the power 5, right? So it's a huge difference between the radius of the nucleus and the radius of the atom. Right? So these were some of the important conclusions of Rutherford's model of atom, and this laid the basic of how we see the structure of an atom today, because these things which Rutherford found with the help of his gold foil experiment turned out to be extremely useful for later studies. So Rutherford's model of atom was finally defined somewhat like this. The positive charge and most of the mass of the atom was densely concentrated in extremely small region. This very small portion of the atom was called nucleus by Rutherford. So Rutherford was the one who, in a way you can say that he was the one who discovered the nucleus. I mean, he was the one who told that, okay, inside the atom you have the positive charge in a small region, that region is nucleus, right? He was the one who told that the nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called orbits. Because he experimentally found that only small region was dense, and that was nucleus. Rest of the region was all empty. But since the atom was electrically neutral as a whole, so that means if you have a positive charge, there has to be some negative charge, and those negative charges were electrons. So he told that the electrons were moving in circular paths in that empty space, and these circular paths are known as orbits. So Rutherford's model of atom resembles the solar system, in which the nucleus plays the role of the sun and the electrons that of revolving planets. Like how in our solar system we have the sun and all the planets revolving around the sun. Similarly, you have the nucleus and all the electrons revolving around the nucleus, right? So this was Rutherford's model. He told that the electrons and the nucleus was held together by electrostatic forces of attraction, right? So Rutherford's model of atom was very similar, or it was analogous to our solar system, right? So many times, since Rutherford was the one who spoke about the existence of the nucleus for the first time, therefore Rutherford's model of atom is often known as the Rutherford's nuclear model of atom. Because before Rutherford, it was Thomson who did not talk about nucleus at all. He just told that positive charge is there everywhere inside the nucleus. So according to him, the atom is dense everywhere. Again, prior to him was Dalton, who even did not mention anything about the constituent of the atom. He just told that atom cannot be divided further, right? So it was Rutherford who came up with a very important conclusion, right? Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again. Hello friends, this video on atoms part 5 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 4 before going ahead with part 5. So now let us talk about the electron orbits. So the two important things which Rutherford told us was, one was nucleus. He told us about nucleus, and the second was the electron orbits. So we have already discussed about the nucleus part. So now it is time to discuss the electron orbits. So what did he tell about the electron orbits? So according to Rutherford's model, nucleus was at the center and the electrons were revolving around it. So there was a force between the electron and the nucleus, as I mentioned in the previous slide, that why are the electrons held in those orbits? It is because of an electrostatic force of attraction between the nucleus and the electron. So what is this electrostatic force of attraction? It is denoted as Fe. Now since this is my nucleus and this is my electron, which is revolving somewhat like this, so there is one electrostatic force of attraction, but at the same time, since it is moving in a circular orbit, there is a centripetal force. So this electrostatic force of attraction gets balanced by the centripetal force, right? Now, what is the electrostatic force of attraction? It is nothing but given by Coulomb's law, 1 by 4 pi epsilon naught into charge on an electron, that is E, into charge on the nucleus. So let us denote the charge on the nucleus as Ze divided by R square. So this is equal to the centripetal force, which is nothing but mv square by R. So this R and this R will get cancelled. So from this we can say that R is equal to Ze square divided by 4 pi epsilon naught into 1 by mv square. So from this we can say R is equal to Ze square divided by 4 pi epsilon naught mv square. So what is this? This R is the radius of the orbit in which the electron is moving. So often this R is known as orbit radius. And what is this V? This V is the electron velocity. That is the velocity with which the electron is moving around the nucleus, right? So this is how Rutherford defined the orbit of an electron. That he told that electrons will move in orbits. So what would be the radius of that orbit and with what velocity the electron would be moving would be given by this expression. So now from this expression, he also evaluated the kinetic energy associated with the moving electron. So the kinetic energy denoted by K is nothing but half mv square, right? So this will be half m into v square. So what we can write V as, so from the previous expression of orbit radius, we can write velocity in terms of radius r. So this will be Ze square divided by 4 pi epsilon naught mr. So this m and this m will get cancelled. So we get Ze square divided by 8 pi epsilon naught r. So this would be the kinetic energy associated with the moving electron. Now let us talk about the potential energy. Potential energy denoted by U is given by 1 by 4 pi epsilon naught into Q1. Q1 is the charge on the electron, into Q2, that is the charge on the nucleus. So this charge is positive and this charge is negative, right? So this divided by R, that is R is the distance between the electron and the nucleus. So this comes out to be minus Ze square divided by 4 pi epsilon naught R. So this is the potential energy associated with the system. So now that we have calculated kinetic energy as well as potential energy, we can very well calculate the total energy. So what would be the total energy involved? That is kinetic energy plus potential energy. It comes out to be Ze square divided by 8 pi epsilon naught R plus minus Ze square divided by 4 pi epsilon naught R. So this comes out to be minus Ze square divided by 8 pi epsilon naught R. So this is the total energy associated with the electrons. Now, what do we observe from this? We see that the total energy has a negative sign with it. What does it show? This shows that the electrons are bound to the nucleus. Had the total energy been positive, in that case it would have meant that the electrons are not bound to move in the orbits. They are free and they can move anywhere, right? So this total energy calculated by Rutherford also supported his observation and conclusion, because he had told that electrons move in orbits. So this calculation of total energy also supported his statement that since the total energy is negative, that means the electrons are bound to the nucleus and they are bound in this electron orbits, right? So now from this, what do we observe? If you look at these three expressions of kinetic energy, potential energy and total energy, you would see that kinetic energy is nothing but negative of total energy. I mean, magnitude of the kinetic energy and total energy is the same. So you can say that kinetic energy is negative of total energy. Similarly, if you compare the potential energy with the total energy, you can see that potential energy is twice of the total energy. So you can say that potential energy is equal to twice of the total energy, right? So this was all that was told by Rutherford regarding the electron orbits. So this was Rutherford's model of atom. Now this Rutherford's model was able to explain many things successfully. It could explain the existence of nucleus, the arrangement of electrons, the electron orbits. So it could explain plenty of things. However, this model also had certain limitations. So let us look at the limitations of the Rutherford's model. The first limitation was it could not explain the stability of an atom. Why it could not explain the stability? Because Rutherford told that electrons are moving around the nucleus and it is moving in orbits because it is balanced by the electrostatic force of attraction. Now, electrons should be attracted by the positively charged nucleus every now and then, right? So now, according to the electromagnetic theory of Maxwell, if you remember your lesson on electromagnetic waves, you'd remember that Maxwell had given his theory stating that charged particles, when accelerated, they emit electromagnetic radiation. So this was a theory which was very well proved and given by Maxwell. He told that whenever there is a charged particle which is accelerated, it will emit electromagnetic radiation. So now if you look at these electrons, what are these electrons? They are charged particles, negatively charged particles. They are also getting, since they are getting attracted by the nucleus, so they are also getting accelerated as they are moving on their circular orbits. Therefore, these accelerated negatively charged electrons should also emit electromagnetic radiation. Now, if they are emitting electromagnetic radiation, then what's happening? In that case, the orbit of the revolving electron will keep on becoming smaller and smaller, following a spiral path, and ultimately the electron will fall into the nucleus. This is what it should happen. Let us suppose if this is my nucleus and if this is my electron. Now, Rutherford told that electron moves in this orbit, right? Now, if this electron is, but he did not consider the emission of electromagnetic radiation. But according to Maxwell's theory, this electron being a charged particle, it is getting accelerated as it moves in this path. So it should emit some electromagnetic radiation. That means some part of its energy is lost in emitting this radiation. So as a result, this electron's radius will keep decreasing and gradually the electron will fall into the nucleus. So that means the atom will not be stable. But that is which doesn't happen actually, right? I mean, in reality or in nature, you see everything which is around yourself is made up of atom and things are stable, right? So that means there is something which defines the stability of atom, which Rutherford's model could not. So this became a very big limitation of Rutherford's model. Also, it says nothing about the electronic structure of atoms, that is about the distribution and relative energies of electrons around the nucleus. Rutherford just told about the path followed by the electrons. He did not talk about like how many, I mean every atom, when we talk of an atom, it does not consist of one electron, right? There are plenty of electrons. So Rutherford never spoke about the distribution of those n number of electrons. He just told that every electron will move in an orbit. But when there are 100 electrons, how will those 100 electrons move in different orbits? Whether they will move in 100 different orbits, or they will move in one orbit, or how will they get distributed? So he did not talk anything about that. So distribution and relative energies of electrons was not at all explained or discussed by Rutherford. Dual nature of electromagnetic radiation could not be explained. As you saw in our previous lessons, that there were several experiments which proved that dual nature of radiation is true. That means every particle can behave as a particle as well as wave. Similarly, every wave can behave as a particle as well as wave. But Rutherford's model could not explain this dual nature. Experimental results regarding atomic spectral emission lines could not be explained. Now, what are these atomic spectral emission lines? We will talk about them in detail in the next few slides. So these spectral lines are a very important concept in science. I mean, they are extremely useful in different research work and all. So this Rutherford model of atom could not explain anything about this spectral lines. They could not explain why these spectral lines occur. Right? So these were some of the limitations of Rutherford's model, because of which it was not a full proof, or it was not completely accepted. However, it told many things which were correct. I mean, it was the first model to at least give an idea of the correct picture of atom, right? But there were so many disadvantages as well. So in order to overcome these disadvantages, came up the next model, that was the Bohr's model of atom. So now, before we get into Bohr's model of atom, let us understand what is atomic spectra, because here I mentioned you that it could not explain the atomic spectral emission lines, right? So before I introduce the Bohr's model to you, it is good if you understand what is atomic spectra. In that case, you will be able to understand the Bohr's model in a better way. So what is atomic spectra?
Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.